Hey, Algebra 2 Honor students, this is going to be your Unit 11, Day 4 notes, and we are on page 13 of the packet if you want to open it up to that page. What I'm hoping you're going to see today are some exponential applications that look pretty familiar from what you studied in Algebra 1, but we're going to push this and extend it a little bit further in terms of some other formulas and some other derivations of this equation right here that we can use to model exponential growth and also exponential decay. You know, certain things decrease at a fixed rate over time, so we'll talk about that as well. So to get started, we have the formula y equals a times 1 plus or minus r to the t power. And what I want to do is just off to the side here, define some of those variables for you here. So on the left side where we have y is the final amount of something. And that final amount could be, you know, the final amount within a population. It could be the final amount of, money in an account that's growing at a fixed rate. So that final amount could be representative of a few different things. All right, capital A is going to be the initial amount that you start with. And then the last two variables we have to define are the values of r and t. R is the rate of growth. And the rate in our questions will always be given as a percent. And we're going to take that percent and very carefully just make sure we convert correctly to a decimal. Okay, we're going to move the decimal place 2 to the left to go from percent to decimal. And then finally, t is time. And t is usually time in years, but it doesn't have to be. T, we're talking about, for example, bacterial populations. Those are going to grow most likely very quickly in an hourly fashion. So I would say most commonly t is time in years, but that's something we'll just want to pay attention to. The last thing I'll say is just keep in mind that that plus or minus would depend on if it's exponential growth over time, or on the other hand, exponential decay. So we have to read the question carefully, especially when the model's not given to us to determine whether we're dealing with growth or whether we're dealing with decay. The first example, the model will be given to us. So it says an exponential model for the population of Indonesia during the 1980s is given by this equation right here. P equals 148.7 times 1.021 to the t. And t is kind of important to pay attention to. It's the number of years after 1980. So it says, in this decade, what was the annual growth rate of Indonesia's population? So to figure out the annual growth rate, we want to analyze that number in parentheses and know that some value 1 plus r already happened. So basically, if we take that decimal on the inside and subtract out 1, because 1 was added to some rate, that's going to leave you with 0.021. And 0.021 as a percent, it's actually even working backwards from what we typically do in these problems. We're going from decimal to percent. That shows me that there was a 2.1% growth rate annually during the decade of the 1980s. Good decade, if you ask me. All right, what was the population of Indonesia in 1980? There's two different ways to approach this. 1980 is the initial year, and we define what the initial amount is. Up here is being the capital A. It's the number outside the parentheses. So the initial population is 148.7, and this number is in millions. So we just want to make sure that we're labeling the answer correctly. The other way to think of this is that if t is the number of years after 1980, 1980 is t equals 0. So you could go to the population equation and plug in 0 for t. Oops, let's actually do that right now. And if I plug in 0 for t, anything to the 0 power we know is 1, which then gets me to that answer, 148.7. Okay. What was the population in 1987? So in 1987, how many years after 1980 is that? That's the important piece. If t represents that, then t would equal 7 in this instance. So we're going to go ahead and plug in 7 for t and figure out what the population was in 1987. Definitely need the graphing calculator for a lot of what we'll be talking about today. So now's a great time to find that. 148.7 times 1.021 raised to the 7th power is 171.98. So if we were going to round this to the nearest 10th of a million, I guess that would round up to 172.0. But that many million people is what we would expect according to the growth rate of 2.1% annually through the 1980s. And the last part says, well, determine how long it will take for the population to reach 155 million. Now, think about what we just calculated in the last answer. We know that 7 years later, the population is 172.0 million. So we know it's going to take less time for the population to reach this amount. But population is kind of a Y value in our case, right? It's an output. We have to figure out what input for T would get us this output. So we're going to do 155 equals 148.7 times 1.021 to the, I'm going to call it X just for now, because I'll tell you the only way we know how to do this as of this moment, okay? Because we will eventually learn how to do this algebraically. But the only way we know how to do it right now is graphically. So there's going to be a case for y1, y2, and we're going to calculate some intersections there. All right. Go ahead and enter into y equals your equations here. So we got 148.7 times 1.021 to the x. Y2 is 155. And before I go to hit graph, I want to really make sure I set my window correctly, because x is representative of time. I definitely have to go out, don't have to go out to 100 years. We know what's happening before 7 years is up. So you know what, maybe I'll just set the x max to 10. You could even make the x max 7 if you wanted to, but I'll go out 10 years just to kind of get a good scale for the x-axis. Now for the y values, we probably don't need to look at any negative y values. We're looking at population here. But we need to at least see when the population is going to reach 155. And of course, this number is in millions, but because we're talking about numbers in millions, a y max of 500 probably is sufficient. Maybe I'll even bring it, excuse me, down to 200, and that would be just a tighter window for us to see this graph sketched over. So at this point, if you have the window set the same way that I do and you hit graph, let's see what happens here. Happens pretty early on, right? And it's a very slow rate of growth here. 1.021 as a base of an exponential, it's definitely pretty slow growth. If you were to extend out the window, you might see a little bit more bend in the curve there, but let's calculate that intersection point. Second trace, we're going to calculate the intersection. And the intersection point here is 1, 2, 3 at 1.9965. Okay. 1.996, I mean, that's really close to 2 years later. So I'm going to say approximately how long will it take? Let's say the time is 2 years later. So for questions of this form, especially applications, you want to look at directions as far as rounding. Sometimes we can even round populations to a different amount. You know, years, you can have decimals of a year, of course, right? You can have 1.99 years later. It's almost 2 years. So if I said round to the nearest 10th or 100th of a year, I could, in this example, also have asked, in what year will it happen? Because we have a starting year. Now, I just said, how long will it take? The answer is, in fact, 2 years. But if I had said, in what year will the population reach this amount? You would have answered by saying 1982, because that would be 2 years after 1980. So just kind of keep that in the back of your mind that there's, although we can, I think, calculate this pretty easily with y1, y2, we want to make sure in the end that we correctly answer the question, whether it involves rounding or thinking back to an initial year and then adding the 2 years onto that. Okay. Moving on to number 2, we're going to save this one for class. So this is a good example of a medical case where a patient is given some penicillin and it's decreasing at a fixed % per hour. Okay, so like we said earlier, time could be in hours, does not have to be in years. But we'll go over this one in class. This one we're going to develop a model for and be able to answer some questions. I want to get into number 3 on the next page, which says, suppose you deposit $100 into an account that earns 5% annual interest. If no withdrawals are made, how much money is in the account at the end of 4 years if the interest is compounded annually? When we're talking about compound interest follows pretty much the same formula that we used on the front. So y equals the initial amount A times 1 plus r to the t. Now, when we're talking about growing money, we usually don't have a minus in there, right? So it's always going to be 1 plus the rate to the t. Let's plug in what we know to figure out the final amount y after 4 years. So y would equal, in this case, $100 times 1 plus the rate. Here we have to plug that in ourselves. So 5% is 0.05. Be really careful about that, because if you plug in 0.5, you're giving yourself a 50% interest rate, which is much, much better than 5%. That's going to get raised to the t, which is to the 4th power. So let's see what this comes out to be. Now, you don't have to necessarily do any math in your head to add the 1 plus the 0.05, but I mean, let's face it, that's pretty easy in this one at least. It won't always be maybe that nice of a situation we'll encounter, but if I raise that to the 4th power, we wind up getting $121, and with money, unless it says otherwise, I always round to the nearest cent, so that would be 55 cents, $121.55. So in 4 years, how much money have I gained? Not very much. I mean, we made $21 in interest and 55 cents, which is better than nothing. But certainly if you're looking to gain a lot of money over that time, you really haven't made too much by just letting your money sit in the savings account here. All right. So in part B, it says the exponential function a equals p times 1 plus r to the t is really applied to investments that represent interest compounded annually. So even though I wrote this formula from the front, this is just using different variables. And the only thing that's really, I guess, very different is A is the final amount. We use capital P when we're talking about something called the principal, not like Mr. Clark, the principal, but the principal stands for the initial investment that you make. And then everything else is pretty much the same. So some accounts will apply a portion of the fixed annual interest rate multiple times per year. I'll have you think back to mortgage calculations. You get an annual interest rate, but you're making the payments on your mortgage monthly. So think about what we did in those mortgage payment questions to figure out the actual rate of interest there. So what if we go back to the annual interest rate of 5%, but it's compounded, that's going to be a new big word, monthly. What happens is that we get 5% over 12, or 5/12% is paid to you 12 times per year. So it's not that you're getting 5% rate 12 times in a year. That 5% is divided by 12, split into 12 little pieces, and you're given a little bit of interest each month so that by the end of the year, you've earned 5% interest. But it's applied to your account in a different way. So this is how we're going to determine how much we have after 4 years. The amount A, I'm just going to try and use a formula similar to these variables up here, would be the principal of $100 times 1 plus, now we have to take that rate and we're going to divide it by 12 because we're getting monthly interest. Now, if you think about applying interest monthly for 4 years, how many monthly interest payments do I get in the course of 4 years? This is a calculation we've seen with those mortgage payments. Well, if I do this for 4 years, 4 times 12 is going to be an exponent up here of 48. So we're not raising that to the 4th power because we're looking at a monthly situation. Now it's to the 4 times 12. And the amount of money that I would have after that time, 100 times, here's where you don't have to know what 0.05 over 12 is. You can just type that in, right? 1 plus. If you want to do a fancy fraction, that of course would work as well. You don't necessarily need it here. But raise that to the 48th power, and we get $122.09. So it is a little bit more, but not even $1 more 4 years later. Okay. So I will tell you that the more often interest is compounded at a given rate, the more your money will grow. But in this scenario, because the initial investment's pretty small, we're only doing it for a small amount of time, the interest rate, maybe is not very large. We don't see a huge difference between interest compounded annually versus compounded monthly. Okay, so there's going to be a different formula that we use when interest is compounded n times per year. And the formula that we're going to use is A equals the initial investment P times 1 plus. We're going to take the rate and divide by n, where n represents how many times per year the interest is applied. Okay, so you'll notice here that we took the rate for compounded monthly and divided by 12. That's going to be raised to, how did I get the 48 up here? I took the value of n, which was 12, and we multiplied it by the time of 4 years. So the new exponent in this formula is nt. And you can use this one solely if you'd like to when you're talking about compound interest, because even if it was compounded annually when n is just 1, you're going to get back to this formula right here if n is 1. So if you want to kind of like skip this one for talking about compound interest and just kind of know this one's pretty important, because if interest is compounded any other way, we've got to know this formula here. So let's talk about the same situation up above, but if interest is compounded semi-annually. Semi-annually would imply that we're getting it twice a year, so n would be 2. So the amount would be 100 times 1 plus the rate, 0.05, divided by 2. And if we're doing this for 4 years again, it would be to the 2 times 4 power. So of course you can clean some of this up in your head, right? You could do the 2 times 4 is 8. Let's see what we wind up getting here. So 100 times 1 plus 0.05 divided by 2 to the 8th power is $121.84. So notice how semi-annually it's less than monthly, but it is more than annually. So it makes sense that we get a value that's an answer that's somewhere in between. If interest is compounded quarterly, you're going to get that the value of n should be 4. So 100 times 1 plus 0.05 over 4 to the, in this case, 4 times 4 power, so to the 16th. You can cheat a little bit and either go up and highlight that answer, or do you guys know second enter will bring up what you just typed in? Maybe that's a quick way to do this. Change the denominator to 4 for compounded quarterly, and the new exponent to 16. Here's the amount that we have, $121.99. Okay. Well, we're going to make a big jump here. Remember what it was? Let's see, this was for monthly. We're going to daily. What if interest was applied to your account every day? You would take your rate and divide by 365. So now the amount is 100 times 1 plus 0.05 over 365, all to the 365 times 4 power. Oh, man. All right. It seems like it's going to be so much more, but think about that. You're taking 5% and cutting it into 365 tiny, tiny pieces. This one might be easier just to kind of type in all over again. So if I divide the rate by 365, make sure you change the exponent to 365 times 4. It's really not that much more. It's only in 4 years, the difference between these two accounts is a total of 15 cents. Now, granted, I would like an extra 15 cents if somebody was going to offer it to me. So I guess I would choose this account over that one. But you can see how it's not that drastic of a difference. In fact, I'm not going to do the whole calculation for hourly, but how many hours are in a year? Take the number of days times 24. It's 8,760 hours. If you replace the n value with 8,760, there is no change in the hundredths place of a decimal. So you're still getting really that same amount of money, even if interest was compounded hourly. But where we're headed with this whole discussion is, what if interest is compounded not every hour, but every minute of the day? Or what if interest is compounded not every minute of the day, but every second of the day? And we're going to cut that interest rate into such tiny, 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 tiny little pieces that eventually it's kind of like splitting it up into an infinite number of pieces. Well, the thing is, we can't plug in infinity for the denominator. Calculator's going to have no idea what to do with that. But there is a mathematical expression that represents what happens to this formula as n gets bigger and bigger and bigger. So if we turn to the next page, what we're going to see is we're going to have a new number added to our number system right now. It's the number e. And the number e is a mathematical constant similar to pi that is used to model growth and decay that is changing continuously. So when interest is compounded continuously, not just monthly or daily or whatever it might be, we see that this continuous change, the base of the exponential, becomes this number e. It is sometimes referred to as natural growth and decay. So it's going to be weird for us because e just looks like a variable, but e is actually a number. If you go to your calculator and hit second division sign, find it, second divide, you'll see a little e pops up on your calculator. You hit enter, and guess what? E is a number 2.718. Now, when I say that E is a constant similar to pi, what you should be thinking about then, if E is similar to pi, is that this is an irrational number. So it almost looks like the decimal repeats based on what you're seeing on the screen, but that's not true. So what happens is that the formula changes a little bit if you're dealing with interest that's compounded continuously. Compounded monthly, daily, quarterly, semi-annually, you're going to go back and use this formula right here. But as this expression, as n approaches infinity in this expression right here, what happens is that base turns into approaching this value of e, which is a crazy concept, I understand. The formula I think you'll find is actually quite easy to use. So suppose that $1,000 invested at an annual rate of 8%, compounded continuously. Those are words you're going to have to, as soon as you read them, underline them in the question, because when I see compounded continuously, I know I'm going right away to writing down the PERT formula. It's fun that it even has a little name, right? PERT. P is the initial amount still, R is the rate, T is the time. The only thing that's different is that E is the base of the exponential, and it's a number. It's 2.718. The calculator knows it. Okay, so find the amount in the account after 10 years if no withdrawals are made. So if it's compounded continuously, we're going to plug in that the initial investment's 1,000 times the base E to the rate of 8%. Please make sure you plug in 0.08 there. And then the time is 10 years. That's 10 right here. And this is just going to be something we type into the calculator. So 1,000. And then E to the, type in 0.08 times 10 up there. Again, you don't even really have to do much of the math in your head. Calculator will do it for you, $2,225.54. So we've more than doubled our investment 8 years later. Oops, I copied that wrong. I don't know where I got that number from. $2,225. The 54 cents is at the end. I was like, where did that number come from? All right, that's the amount that we're going to have 10 years later. So yeah, still a little bit more than double what our initial investment is. Part B, how long before the account grows to $3,000? So what I want to know is how long. Well, I'm looking for time when the amount is 3,000. So we're going to plug in 3,000 for the amount, 1,000 for the initial investment still. E to the, well, we're not changing the rate of 0.08, but we are solving for time here. So just like we did earlier, the only way we know how to solve this right now is by doing y1, y2 on the calculator. So I'm going to come back over here, clear out the initial model. So 1,000 e to the 0.08x, and in y2 we're going to type in 3,000. Let's see, what do we know? We know that in 10 years that the amount was this much. So it's going to take more than 10 years to get to $3,000. And the reason why that's important is when I go to window, right now my X-max is at 10 years. I'm going to go out to 20 years. Hopefully it happens by then. If not, I'll extend it out a little bit further. We're looking for the amount, the Y value, to be 3,000. So we got to go at least up to 3,000. Maybe I'll go up to 3,500 just to give myself a little bit of breathing room at the top of my screen. Hit graph. We're going to see that exponential. Looks like 20 was a good choice on our parts here, or at least my part. You're following along and you would have guessed it too. So we're going to do second trace, calculate that intersection point, and it appears that the time it takes is 13.732 blah, blah, blah years. Now, there was no rounding directions here, but I promise you on a test or quiz, I'll do a better job of giving you some more specific directions. Let's go to the hundredths place, 13.73 years. Because what's going to happen is, yes, by the 14th year, it's reached this amount, but you can walk into the bank sometime during the 13th year, pretty close to the end of the year, and walk in and your account will have reached that amount of money. Okay, so this whole idea, this new formula with compounded continuously, I realize it can throw us for a loop at first, but I'll tell you this model is not only used for financial applications, it's used for naturally increasing or decreasing populations. So we'll save this one for class tomorrow as well. I know we have the one at the beginning of the notes, and then here's one as well. But the key idea is if your population naturally is decreasing continuously, that's another hint that I need to use this new PERT formula right here. Okay, so we'll do that one tomorrow, and we'll do a quick recap and get you guys ready for for some really good exponential application practice. Okay, so that is it for today's lesson. Have a great rest of your day.